Welcome. My name is Erin Akred. I'm a data science manager at DataKind, and I'm leading the learning and synthesis portion of our projects with the Omidyar Network. I'm going to start by addressing logistics. In this presentation, I'll be leaving a few opportunities to ask questions. You may have noticed that you don't have microphone access, but we will be using the Q&A functionality in Zoom today to surface your questions. So as they come up, feel free to enter your questions for me and the project team there, and we'll address them throughout this presentation. Now, without further ado, DataKind and the Omidyar Network have kicked off our partnership with a design session intended to uncover pain points in the extractives industry. Together with Omidyar Network investees from the Columbia Center on Sustainable Development, Global Witness, Natural Resources Governance Institute, Open Oil, Publish What You Pay, and Transparency and Accountability Initiative, we sourced the projects we'll be talking to you about today. At the first webinar in August of last year, we came together to discuss the learnings from scoping the projects. We talked about the 6 components for successful data science for good projects, and how it takes a village to leverage advanced technology for good. A second webinar was held in October to share learnings from the exploratory data analysis and initial modeling phases of doing data science projects for the extractives industry. You can listen to these recordings following the link from DataKind's blog. Now, the 2 projects have just wrapped up, and we've brought you all together today for our final webinar, where we'll discuss findings and what was learned, or relearned really, in the process. Our hope is that our partners and webinar attendees will have a new understanding of how data science capabilities might help them operate more effectively and efficiently to combat government and industry corruption, learning what they have at this series of webinars. DataKind has a history of choosing challenging, cutting-edge projects in new spaces. Sometimes we develop adoptable solutions, but sometimes a proof of concept to advance the field is our intent, as it was for these 2 projects we'll be discussing today. For example, when we can think about data not just as dry numbers contained in surveys, and think instead of satellite imagery as data, which DataKind did with DataKind Give Directly, a whole world of possibilities unfolds. So today, for those new to the webinars, I'll briefly reintroduce the 2 projects that DataKind did with our partners, discuss findings, and then I'll talk about how DataKind and our partners' major takeaways from the work together. The first project I'll discuss was led by Jackie Weiser. It is important because it can help the professionals working in the extractive industry governance, like our partners at National Resources Governance Institute, or NRGI. These folks aim to help local communities benefit from their country's endowments of oil, gas, and minerals. One of the tasks to achieving those benefits is by assessing lengthy extractives industry legal contracts for things like fiscal governance and environmental reparations. But this is a time-consuming, manual, and subjective process. If effective, programmatic labeling of certain clause types could enable those reviewing the contracts to benefit from data science processing, as it could, taking natural language cues from the text, highlight likely relevant contracts and relevant content within the contracts. If a signal exists and a well-tuned model is developed, the labeling might ultimately need only minimal human correction. In addition, a higher level assessment than word-for-word comparative review might be possible if machine learning techniques could pick out what is different in one contract compared to a template contract. These are the challenges Jackie, Yvonne, and Chris, the 2 other data scientists on the project, set out to answer. So for this project, we leverage publicly available extractive industry contracts to extract data to assist legal reviewers, journalists, regulators, and community activists with functionality as follows. Suggested tagging of certain types of clauses like stabilization clauses or royalties clauses. Identifying where and how a given contract differs from a template contract. and additional metadata like named entities, language detection, and general text mining statistics are now available for all contracts. What's showing on this slide on the left is an example of some of the text from one of these Extractives contracts, with certain areas highlighted as important and clauses that are worth looking at when reviewing for stabilization and royalties. What we're showing on the right of this slide is a list of contracts from the Philippines. We know that in the Philippines, you do use template contracts. So what we would like to do is to be able to compare each of these contracts with the template and highlight what is different. These were the two tasks that we set out to do for the first project. What was the approach we took? On the next slide, you'll see a diagram of the data processing techniques. The first task was to ingest a full corpus of data. Then we went to the modeling. We trained a random forest classifier to detect royalties and stabilization clauses. The model was trained on all available human annotated clauses using clause features like language, bigrams, trigrams, part of speech tags, sentiment, and average word length. Next, the team tuned the model for performance to minimize false negatives. And then we gut checked the most important features that were predictive of this type of the clause type. With that model, the team then took the rest of the corpus that was unannotated and ran optical character recognition on the PDF documents. The unannotated contracts were parsed by paragraph for prediction, which is shown on the left here. And all the clauses were passed through the model and labeled with either stabilization, royalties, or other tags. NRGI manually checked false positives and provided feedback. For example, they expected the word percent to be an important feature in calculating in determining if something was a royalties clause, so that was hard-coded into the model. We then further tuned the model to incorporate feedback from analysis of false positives by the subject matter experts at NRGI. The team determined that false positives would be much preferred to false negatives for similar reasons to why this would be preferable in a cybersecurity setting. We want to be sure we don't miss anything. So while accuracy suffered a small amount, the model was tuned to favor false positives over false negatives. Finally, we held a meeting yesterday to discuss the capabilities that had been shown and reiterated that these results were early and needed several additional iterations with the adopters and subject matter experts in the loop before we could report on any efficiency gains. On the next slide, I'm going to show you some findings from this effort, where we tried to predict one of 6 different labels, including operations, environmental provisions, and other. What we're illustrating here is what is known as a confusion matrix in data science. The matrix is populated and color-coded according to what the actual and predicted counts are from the model. So for example, on the top row, we can see that the model is predicting correctly 633 environmental provision clauses, but that in 68 cases, which is the rest of the top row, what the rest of the top row sums to, the environmental provision clauses are being mispredicted, mostly as other clauses in the case of 59 of those events. Little tuning was done on this 6-class model prediction. I've just chose to show this one compared to some of the other models we built because the signal shows up fairly clearly. One can observe the darker band from the top left to the bottom right in the confusion matrix, indicating that there is a signal that the model is picking up on. We also saw evidence that major languages like English, Spanish, and French were not an issue in our model, but languages like Arabic, of which some of the contracts were in, couldn't be processed by the libraries we were utilizing. And then in terms of the predictive features, random forest models are able to indicate what these are, but are not able to provide directionality of impact in general. In the chart on the right of the slide, we can see above the stem that the stem of the word pollution is likely indicative of discussion of environmental provisions. but the stem of the word prudent could indicate something other than environmental provisions is being discussed, which is what we're trying to get at by claiming that these features are not, or stating that these features do not indicate inclusion or exclusion. This is the end of the results discussion of this task, but we also attempted to use the same data set at finding clauses to detect as the finding clauses effort to highlight where contracts differ from a template. For this task, we ran optical character recognition on the PDF documents and cleaned the corpus. Then Raven fingerprinting was used to hash the document into chunks that each of the features in the full contract. The team ran a hierarchical network-based unsupervised learning algorithm, where we could assume that the cluster centroids would be most representative of the cluster as a whole, and that cluster outliers would vary from the most representative in some way. Then, if necessary, we could flag the cluster centroids as templates if we didn't have any other indication of what the template contracts were. We highlighted outlier documents that deviated from those centroids and provided a list of contract IDs, template flag, cluster IDs, and the anomalous content. We had NRGI spot check the English language contract for template flagging. What we're showing on this chart in this slide is called a dendrogram, and it illustrates that clustering that was done on the contracts. We can see at the highest level over on the right side of the diagram that there were approximately 4 different high-level clusters that we could come up with, and those we would think would correspond to language or resource of the contract and interest. Unfortunately, this is as far as we got on this exploratory task. We determined that while this would be an interesting use case of data science for the extractives industry, that getting to a place where we had a workable model was out of scope for the current effort, so we pivoted back to the clause identification task. We learned a lot in the process of doing this project, but the takeaways that were most significant were, first, that data scientists are skilled in their craft, but they don't necessarily have the awareness that could be obtained from the subject matter experts. In the first webinar, I discussed the importance of subject matter experts in all DataKind projects. And in this case, we're still realizing after a couple of iterations that there's more to codify in our models. Second, if we want to quantify efficiency gains of the solution, we must first establish what baseline performance is. One of the observations we had in our meeting yesterday was that when we look at these, when we say that we're getting an efficiency gain because we can pre-label different clauses with labels from the annotations, that we still are missing the concept of how lawyers review these contracts. So we need to establish a baseline to understand if and where there were efficiency gains. Next, what stands between an interesting solution and adoption is often a design challenge. And I'm actually going to go on mute here to cough real quick. In this case, we were able to come up with different contracts that were outliers, and in some cases, what clauses were outliers as well. We asked our partners at NRGI to look through the spreadsheet that we had developed to try to better understand where our model was performing well and where it wasn't performing so well. This spreadsheet approach was not very effective, and were we able to build a user interface that said, this is where what the model predicts, and here's what the model is actually giving, that the user might be able to then select whether the model is correct or right with a toggle button, and this would be a much better user experience. Fourthly, what we wanted to accomplish was to speak in a common language with our partners. Basically, this gets back to the vocation versus advocation. Our data scientists are highly skilled at their craft and speak in a very specific language, which is the same with the partners who are legal experts and speak in a very specific language for their task. What we failed to do in some cases was speak in a common language, and things like the confusion matrix that I showed you earlier only led to just that, confusion. So it is reiterated, something that we knew that we need to continue doing is to work extra hard to speak in common language as our partners. Finally, we need to be clear about just how much a human is going to be required in the loop of the final solution. If our partners were expecting a solution that would automatically tag annotations and wouldn't need any human intervention, then this solution could be seen as somewhat disappointing. But in our case, we actually tried to be clear that this is a first iteration of prioritized labels that the model can create that we would then need a human to verify. So I'm going to pause here for questions. I don't see any open questions at the moment, but I'll pause briefly to see if anyone has anything that they would like to ask about this specific contract metadata project. Well, folks are certainly welcome to add questions as we go. I'm going to continue in the interest of time on to the next project. So our next project was the following, was motivated by the following. Irregular mining activities are known to have both positive and negative effects. For example, they provide employment to tens of millions of poor and developing countries, and in some cases, they fuel conflict and often are conducted under poor environmental practices. For example, the use of mercury in gold mining. They often lead to mixed social outcomes, child labor, but also higher family incomes. And the insights gained can be passed to researchers and monitoring groups like Global Witness, who can then contact the local groups to verify their presence. To get at social and environmental impact of irregular surface mines, the industry first needs to know where irregular mining is occurring. So DataKind's goal for this project is to successfully train image recognition models to detect irregular mining activity in Landsat imagery. While remote sensing is a well-established method for detecting large-scale phenomenon like elevation, vegetation, or temperature, it is an open question if the same data sources and techniques can effectively recover finer grain concepts such as mines, even in low resolution satellite imagery, which has a resolution of 30 square meters per pixel. This is a challenging task for several reasons, but I will call out three here. Image quality can be low because of obstructions like clouds, which is what we're showing in the left side image. On the right, we have low image resolution. As you can see, the inset image is the satellite imagery that we were using to detect mines, and surrounding it is satellite imagery from Google Earth imagery, and you can see that's much higher quality, but we don't have timestamps associated with that imagery, so we are resolving to use the lower res light imagery. Thirdly, this is a challenge because big data techniques are recommended. We went with relational databases on a single machine, and processing times were prohibitively long. So as one of our recommendations going forward is that we switch to a cluster environment and use up to 100 machines to do the processing that we were doing with a single machine. The approach we took for the project was as follows. Originally, we had planned to use Global Forest Watch concession boundaries, which is essentially a mining permission area, for our training data with a ground truth mine of location, as our ground truth mine of locations. Unfortunately, concession boundaries weren't going to be helpful, as approximately half the surface area of the Democratic Republic of Congo is under concession. So we leveraged the International Peace and Information Service dataset, which has latitude, longitude, centroid locations for each mine. These points were studied under high-resolution imagery, and approximately 200 polygon boundaries around the mining sites were drawn to train the model on what was a mine. The team also included features like distance to water and recommends including features like changes in elevation as a proxy for mine going forward. We ran the model on locations believed to be a mine, not the full country or region, as it would be prohibitive because of the big data issues. And the model will programmatically identify mines that are not part of our training data. With this output, a partner at Global Witness or other organization would need to validate the newly detected mines to confirm the model is functioning as it's designed. Because the reason we're searching for irregular activity mining is to assess conflict or environmental impact, our next task is to mash up these with any available data or arrange for boots on the ground to assess these factors. With a verified model, we could then adapt the process to observe temporal and spatial boundary infractions for the Global Forest Watch concessions. So I wanted to show some of the results from this project. What we're showing on the right is actually the same geographic location at different points in time. What we're seeing here is 8 different points in time. And in some cases, like the top left and, well, the whole left row column is all showing approximately the same detection of mines. But then we can see in the middle row, things break down a little bit. And that might be because we're seeing the satellite imagery is obstructed by clouds. It could be several reasons. But to accommodate that, because we're looking at the same areas and the mine is not likely disappearing and reappearing again after about a month, which is the times difference between each of these snapshots, what the team did was actually average over 5 months the pixel prediction. So their the task ultimately boiled down to building a random forest model to predict whether each 30-meter square pixel is a mine or not. You can see that some of the results from this task, when we looked at individual pixels and didn't do the time averaging that I was discussing, precision and recall were fairly low. But when we did the time averaging, we actually got some very promising results. So what are our learnings from this project specifically? Well, first and foremost is that what we set out to do, which was predict for the entire Democratic Republic of Congo, whether we could understand whether irregular mining activity was happening. Because of the limitations in the computing environment, we were actually not able to make predictions for the whole country, but used the Global Forest Watch mining concessions as guides for where to start our search. We also tried what we ended up developing as our process was actually a parallel approach. Secondly, was actually a parallel approach to work that Santiago Saavedra at Stanford had done in Colombia. We chose the Democratic Republic of Congo for several reasons, weather being a big one, but the very biggest one being the availability of data for this methodology. When we studied when we spoke with Santiago Saavedra at Stanford and talked about his approach, he actually also used a random forest model, which I will discuss in this next bullet point. Like I said, we used a random forest model, but we actually had intended to use convolutional neural nets. The reason these didn't work out is because we didn't have enough training data. As a reminder, our training data was those hand-drawn polygons for mines, and we only came up with 200 of those because it's a very manual process to come up with them. We also couldn't use logistic regression because it doesn't do well with the class imbalance, and as you can imagine, even though half the country is under concession for mine, the actual physical extent of the mine dig on the earth is fairly small. So I'm actually going to pause here to take some more questions. It looks like we have a couple things over on the right. So have we used Mapbox for this? I will actually have to get back to you. I know we used the Google Earth Engine to source all of our data. I don't know if and where Mapbox data was used specifically. I think it was not used in this case, but I will get back to you, Shreya. Campello Antonio asked, have you ever tried to pre-process the image data? Oops. Denoising to removing the clouds. Actually, I will say we were using Landsat 8SIM imagery, and they had several different channels, of which were different colors in the spectrum, but there was also a channel, and I'm blanking on the acronym that they used to describe it, but it actually was a denoised version. It was imperfect, and we developed a bit of our own technique for getting at that, but that was something that we looked into for sure. And deep learning considered for this image classification task? I just mentioned we were not able to use convolutional neural nets because our training data was too small. Leah's asking, at what time period were these images analyzed? Did you ever find seasonal changes in the surrounding vegetation limited the model's ability to pick out mines? So we actually looked at several years worth of data and did time averaging. In terms of looking at time as a variable, instead of something that we have multiple readings and could average from, we actually looked at the individual pixels basically for a single time shot. I will go back to a previous slide I had. In this approach slide, I talk about how once the model is validated, we could look within concession boundaries and try to understand where temporal or spatial infractions come about. So for this task, time was not a variable. For going forward, we know that's something that's of interest to our project partners. Changes in seasonality of the vegetation. We actually picked Democratic Republic of Congo. One sec. We picked the Democratic Republic of Congo because of the fairly constant vegetation and fairly low level of clouds. So when we conclude that this project is possible, it's possible to detect mines with satellite imagery, we're very much speaking about specifically Democratic Republic of Congo and not saying that it generalizes, though I will call out that we did find that a very similar approach was taken in Colombia and it was effective there, but sort of similar situation. There's not a ton of seasonal variation in the vegetation. So Shreya asked, who would be the stakeholder for this project? So as I called out in the beginning, the main goal of the project, and this project was born out of conversations with Omidyar Network, between Omidyar Network and DataKind. And the goal was, where can data science be applied in the extractives industry? Because it's fairly minimally applied at this moment. What we ended up working with specific partners who are Omidyar Network investees, but I would say the stakeholders for the project is the Omidyar Network, who's looking to learn about data science and the crossroads with the extractive industry. Janet asked, do you know of anyone doing similar work in Tanzania, particularly using volunteers on the ground? I do not know of satellite, if the question is about satellite imagery, using satellite imagery to detect mines, I don't know of any work being done in Tanzania. Similarly, if it's more along the lines of DataKind involvement and getting volunteers to pitch in on data science projects, I actually don't know of much of that either, but I will take this question back to my colleagues and see if they have any insights there. So back to the presentation. I was actually going to wrap it up here from talking about the projects, but I'd love to address any additional questions that folks on the line have. Keep them coming. Oh, Janet, that's good to know. Thank you for providing that context. Janet said that they're mapping rural Tanzania on OpenStreetMap with Crowd2Map. I think that would be, depending on what variables are being captured in the data, it could be a data source that could certainly enrich this project. If it's human, I'm assuming from the Crowd2Map that this is a crowdsourcing effort. If it's humans mapping different mine sites, that would be extremely interesting to us. Even if it was humans mapping things like conflict areas or environmental impacts of mines, be they aware of the fact that it's caused by mines or not, that would also be very interesting to us. So we have a question from Anders Peterson. For the contract project, to what degree would a growing availability in the future improve the results? Depends on specifically what you mean in terms of availability. Availability of contracts, we actually have a decent corpus of contracts. The thing that we're most in need of for the contracts project would be folks to look at those false positives that we were coming up with and provide feedback to the model. That would take a couple more iterations before it would result in a tool that a human could use to pre-screen different clause types for them. So we're not necessarily needing more contracts, we're needing more labeled data for that project, would be the answer there. Janet says we have so far been mapping roads and buildings both from satellite imagery and by volunteers on the ground, but also plan to include mine sites. Janet, I would say definitely keep us in mind if you, as this project unfolds. We'd love to see if incorporating some of that data might improve our corpus or our body of labeled data. I think that would help us quite a bit, and might push us over the limit in terms of having enough data to use the convolutional neural nets for the modeling purposes. Alrighty, well, I'm always available at Erin@datakind.org. We will be archiving this presentation up on YouTube along with the 2 others. If there are significant learnings you had for this or any feedback you have on the presentations or questions, Janet, I'd love to stay in touch in terms of the work you're doing in Tanzania to see if this methodology might apply for that geography. Others, I'd love to hear your questions. This doesn't have to be the end of the conversation. So find me at Erin@datakind.org and look for an email in your box with the archive of this presentation to share with your colleagues. I want to thank everybody for attending today. We do have we have one more question. What convolutional neural net architectures do you have in mind if there were enough labeled data? I am actually going to, David asked that question. I am going to put you in touch with the team. I am not an expert in deep learning and don't want to say the wrong thing. So David, if you don't mind pinging me at Erin@datakind.org, I'd love to put you in touch with the team to get that question answered. Thank you to the rest of you, and we look forward to seeing you on a future webinar. Have a great day.